Greetings, hello, welcome to this video. In this video we'll be looking at a physics problem. I'll be looking at problem number 2 in circular motion and some applications of Newton's laws of motion. Alright, so given a problem, 2 wires are tied to the 2 kilogram sphere. The sphere revolves in a horizontal circle at constant speed. For what speed is the tension the same in both wires? What is the tension? That's it. So, what are we given? So we have mass of the sphere, 2 kilogram, and that's pretty much all we have. Weight. So the sphere revolves in a horizontal circle at constant speed. So angular velocity is constant. Therefore, we have no acceleration. Question A. For what speed is the tension the same in both wires? We need to find the speed when the tension in both wires is the same. And we need to find what is that tension. That is the question that follows in B. So let's go right ahead and analyze our problem. What do we have here? We're also given length, which is 1 meter. Okay, so let's call this point A. Call this O. Call this B. And we'll call that C. B, C, O, A. And then after this, just go ahead and draw a geometry. Well, I'll just go ahead and sketch the geometry. Okay, we have a sphere. This is 1 meter. .0 meters. I'm gonna name this A as we did earlier. This is B, that is C, and we name this O. Okay, let me extend A slightly down. Okay, so this is A. Okay, Just imagine in your mind that A has moved down to this point. This is where our sphere is. What do we know? We know that LBC equals to 1.0 meters. And what else do we know? We know this angle. We know the angle there, that is 60. What else do we know? We also know the angle right here. Where is it? Yes. Know that this angle here is also theta. Theta is equals to 60 degrees. Alright, what else do we know? If this is 60 degrees, then this angle here, let's call it gamma. Angle gamma, since it's a straight line, angle gamma is equals to 180 minus 60 degrees. Gives us 120. This is 90. So 90 minus 60, that is 30. Gives us, call this phi, that is 30. This is 90, that is 60. This is 30 here. 30. What is this one here? Well, a triangle adds up to 180, so we would say minus 120 plus 30. That will give me 30. So this one here is also 30. So that's phi. Okay. Cool. So what we are interested in right here, right now, is this distance. We're interested in this distance because we'll use this in our analysis and in our Newton's analysis. This is what I mean. As this sphere is rotating in this circular path, it's drawn to the center by the centrifugal force, which is the component of these two wires, the tensions of these two wires. So it's drawn to the center. So there's definitely going to be centripetal acceleration, and for that we need this length. That's why we're evaluating it right now. Okay, so this is called length AO. Looking at my diagram, if that is 1, if length BC is 1, and therefore length BA or AB is also 1, because the angles are the same. Looking at that triangle, this triangle, it's what? It's an isosceles triangle where this side and that side are equal. Or just to go ahead and prove it for someone that doesn't see it, this is how you do it. Okay, using the sine rule, LBC divided by sine phi is equal to L let's say BA over sine phi. Sine phi and sine phi falls off. Therefore, already from here, you can see that LBC is equals to LBA. Okay, cool. This is just geometry, a geometrical sketch. Geometry. I'm using the geometry to analyze my distances that are needed for my analysis. In our kinematic analysis. Okay. So far so good. I'm liking our progress. For what speed is the tension? Is the tension the same in both wires? So we need to find the tension and equate the tensions for these two wires. To find the tensions, we need to draw a free body diagram for our sphere. So we'll do that now. Okay. So now we are looking at kinematics analysis. Not kinematics, kinetics. Kinetics, we're looking at the forces now. So, where do I have to write it? Looking at the forces, let's do a free body diagram, shall we? Of our sphere. Free body diagram of sphere. From the free body diagram, we'll then find we'll find the tension in the cables. Yeah. Cool. So there's my sphere. There's my tension from my wire. Call this tension T2. Okay. And here's another wire. We'll call this tension T1. Okay. Forms an angle theta with the vertical. This one forms an angle theta with the horizontal. Okay. Now just looking at the motion of our sphere problem does state that it's moving in a circular path, so I'm just gonna trace the circular path like that, and this is where our center, call it O, that's our center. So it's happening here. Let me break this into its component. So indicate this. So from the sphere towards the center, we'll call this our normal axis. Okay, this is our normal axis, and our tangential axis is into the board perpendicular to our to our normal axis. At the same time, we'll have our z-axis, which is in that direction, vertically upward from this view. So that's our z. Okay, so these are the axes that we'll be using. Normal and z. It's plus as it goes upward, and it's positive or plus as it goes in the direction of normal axis. Now we can break these guys into components. We have this component, the normal component for T1, and we also have a Z component for T1. We'll call this component, let's call it T1Z, and let's call this one T1N. In a similar manner, we'll have components for this one as well. This will be the Z component, vertical component, and it will also have one component in the normal direction. Let's call this one T2Z. This one, let's call it T2 normal. Alright, those are components. So from the free body diagram, let's just write down what we know. We know that T2 normal is equals to T2 cos theta, and T2Z is equals to T2 sin theta. And at the same time, T1 normal is equal to T1 sin theta, and T1Z is equals to T1 cos theta. Okay. Alright, cool. So there we have it. Those are components. Yeah. And what else? From a free body diagram, there's a very crucial force that we did not indicate. Let me show you. I'm pretty sure you've seen it. It is Fg, the weight of our sphere. So that force Fg is the weight of our sphere. Alright. Cool. So you will see that I did not indicate vectors on the components. Reason being, these are referring to the magnitudes of the components. So it's not necessary for me to indicate the vectors at that point. Alright, so let's do the fun part now. Let's apply Newton's second law. Let's let's do summation of forces, shall we? In the normal direction, this is exciting. I don't know about you, but me, I'm excited that I'm going to do this. So let's go. Alright, I'm gonna do it. Okay, summation of forces. The normal direction is equals to where we are, mass times acceleration. But which acceleration? You see, as the sphere moves in a circular path, it's drawn or attracted towards the center by a normal acceleration, which is equivalent to the centripetal acceleration. There's a centripetal force pulling the sphere towards the center. Therefore, there is a centripetal acceleration whose magnitude is the same as a normal acceleration. So centripetal acceleration, where we know that centripetal acceleration is equals to normal acceleration, which is equals to v squared over that length, L. From our geometry, we got it as L A O. Yes. Okay, cool. So now let's just continue. So what forces are in that direction? We have T1N and we have T1N and T2N. They're all in the positive direction. So T2N plus T plus T1N all equals to mass times centripetal acceleration. What do we know about T2N? T2N, you know that T2N is equals to that. Okay? You know that. No, that's not T2N. Sorry. T2N is equals to that. It's T2 cos theta. And T1N is equals to T1 sine theta. So, T2 cos theta plus T1 sine theta equals to MAC. Alright, let me also substitute the correct value there. V squared over L AO. Call this equation 1. And let's do summation of forces in the Z direction. Yes, let's go. So summation of forces Z direction is equal to, well, in the Z direction, the ball is not moving up and down, so there is no acceleration in the Z direction. So it will be mass multiplied by 0. Therefore, this reduces to summation of forces in the Z direction is equals to 0. But we do have components in the Z direction. We have T1Z and we have T2Z. So T2 sine theta. So we have, let me just write them down there. We have T2Z plus T1Z. And we also have that force. We also have the weight. Don't forget the weight. Minus Fg equals to 0. About the weight, we know that the weight is equals to mg. Alright. What is T2z? T2z is this one, and T2z, T2 sine theta. We have T2 sine theta plus T1 cos theta minus mg, everything is equals to 0. Therefore, T2 sine theta plus T1 cos theta is equals to mg. This is our equation 2. So, from these two equations, we make T1 subject of the formula and then be able to equate it to T2 and then solve for V. We'll be able to get our V, and then once we get our V, we'll be able to get our tension. Therefore, we'll solve the problem. For this part, for this video, I'll stop here. Come back again. Let's finish the problem that we started. Alright, like the video, subscribe if you are not, and have a nice day.